So now we're going to turn the idea of the derivative into a mathematical formulation that will tell us the derivative of any given function as a limit. So if we're talking about slopes, and in this case, we want eventually this slope, the slope of the tangent line to this point, and we call this point x. If you want this slope, let's go and start out somewhere familiar, and let's go and take the slope of a secant line to this curve. A secant line is simply a line that passes through a curve at two different points. So this is the secant line. So now we know these 2 points, and we're going to define them in a second. If we can get the slope of this line, then maybe that will tell us something about this slope. So if this is the point x, and we'll call this point x plus h. The reason why I call this x plus h is because the distance, the horizontal displacement, the change in x is h. This is just a generic variable used to denote any change in x. And then what follows is that this is x plus h. So then let's go and talk about the function values. What is the value of this generic function as a function of x? Well, we say that's f of x. Because whatever value you plug in here, it'll be just evaluated as f that value. So same thing as x plus h. So up here at this point, this is just the height of the function. It would be f of x plus h. So now you'll notice that if we want to find the slope of this line, well, now we have 2 points, 2 coordinates. In this case, this is x plus h, that's the x value, and then the height is f of x plus h. And this, again, just says for whatever x value you put in, the function generally will be the function evaluated at x plus h. So in this case down here, this corner point right here would be x comma f of x. So now, from algebra, we know how to calculate the slope of the secant line. In this case, this is what we said, this is your x2, y2, and this is your x1, y1. So these 2 points. Well, the slope is rise over run, change in y over your changes in x. So from this formula, we see that the slope is going to be y2, f of x plus h, the height at the point x plus h, minus f of x, which is this height down here, all over your changes in x. So x2, x plus h, minus your f1, which is simply x. So from this, we can go ahead and simplify the denominator, and let's go ahead and write this as f of x plus h minus f of x all over h. So we're almost done. So this right here gives the slope of this secant line generally. For whatever function we have, it will be the value of the function at x plus h, any change in h, minus the function value at x, all divided by h. So where do we go from here? Well, if we want to know the tangent line from the secant line, let's go and consider how we get there visually. How do we go from the secant line to the tangent line? Well, first thing you'll notice is if we keep this point stationary at f of x, and we take this point at x plus h, and we start moving it down the slope of the graph, well, let's go and consider what would happen to the slope of the line. So this first one looks like this, 2 points, and your slope looks something like that. If we move it a little closer, so say we keep this point here, and we move it halfway, from here to here. Well, then the slope is going to be a little less steep. It's going to look something like that, right? So that makes sense. So let's keep going. Draw another one. And this time, keeping this constant, we move it even closer down here. May not look like it, but this is a whole lot less steep, less inclined than this one, which is less inclined than this one, because we're moving this point down the length of the curve. So then what happens when we are on the point, when the 2 points meet up and one's on top of the other? Well, that's going to be this. That is going to finally give rise, because as this point moves further down, you're going to notice that once it finally hits that point, we get the tangent line. So now we just went from a secant line to a tangent line by moving this point in this direction down the length of the curve. How do we now put this into a mathematical form? Well, let's go and consider what we're doing. So in this case, let's go and consider the change in x. Well, that's just going to be h. We said here that this is h. Well, now I moved it halfway, the point. So now this isn't h anymore. This is h over 2, by half the distance. Down here, let's say I moved this a quarter of the way there. So now this change in x that was this is now h over 4. Well, if you imagine at this point right here, this is 0. So the change in h is 0 when this point meets with this point. So let's go ahead and just plug in for h in the slope for 0, because that's what we're essentially doing here to get to this point. But the only problem here is, if you look in the denominator, it's just h, and we can't plug 0 in for h. So you would say, okay, well, let's see what happens if I do it anyways. So f of x plus 0, because h is going to be 0, minus f of x all over 0. And this would give us 0 minus 0 over 0. And that's undefined. So then, how do we get around this? Well, in the limit videos, we always saw that if we can't simply evaluate something by plugging it in and seeing what happens at this point, we can take a limit, and maybe that limit will tell us something about what happens as we approach, is that important word again, approach this. So now we know we can't just simply know what's happening here by direct substitution. We can ascertain some information by looking at the limit. So then let's go and take the limit. The limit, and in this case, we're going to allow h to run to 0, as this is happening here, of our slope expression. So now we have the limit as h approaches 0, f of x plus h minus f of x all over h. So this doesn't do much for us right now, but in actuality, this right here is what's called the limit definition of the derivative. So the limit definition of the derivative. So this expression right here is the derivative. Now, when we have concrete examples of actual functions, because remember, these are just functions plugged in at different values over a change in x. When we start plugging in real functions, we're going to find that this right here, if we say that the function is f of x that we're interested in, this right here will give us another function of x, but we call this one f prime of x. This denotes the derivative. So this is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So this right here is going to give us another function, and that function is related to the first function, because whatever x value we plug in here, that will give us the slope of this tangent line at the point that we're interested in. So if we're interested in the derivative as x is equal to 3, then we would plug in 3 for this derivative function, and it will spit out a value, and that value is the slope of the tangent line at the point f of 3. So this is why the limit definition is so useful, and we're going to see examples of how to apply the limit definition from here.